Okay, let's do it.
If you've been watching these videos in the order in which we recommend, we're about to undergo a bit of a culture shift. Now we're going to start talking about the internet and web technologies. So up until now, we've really been doing a lot of C, and when we've been writing our programs, we have been running them from the command line. That's pretty much how the users have been interacting with the programs that we write. They type something in the prompt, something happens in the terminal window, and then it's done. Sometimes you might have persistent data that remains afterwards, but that's pretty much it. It's at the command line. That's the only way the user can interact. From this point forward, we're going to start transitioning so that the users can interact with our websites. So we're going to be writing websites which aren't written in C, but are written in a variety of other programming languages, including PHP and its sort of helper languages, HTML, CSS, and the like. So we're going to start talking about those things. Before we get into web programming itself, I think it's probably a good idea to take a step back and talk about how computers and humans interact over the web. So this video is really sort of a primer, a basic guide to the internet. Now the caveat here is this CS50 is not a networking class, so what we're going to be talking about here is pretty high level. We're not going to get into any low-level details of how all this stuff works. If you're interested in that, I'd strongly recommend taking a class on computer networking. And we might even tell a white lie or two just for the purposes of making the general understanding clear. So with that said, let's talk about how we interact with the internet. So here we are. Here's us. We're pretty looking forward to getting onto the internet, which, as we all know, is chock full of cats. Now, do we just connect to the internet like this? Well, probably not. Intuitively, you know that, say, for example, when you change your Wi-Fi network on your computer, you don't see one called Internet, unless that just so happens to be the name of your local Wi-Fi. Right? It's usually something like Home, or if you're at work, it might be the name of your company. There's not just one option called Internet. And so something or some things exist in between when we want to connect to the internet. What are some of those things? Well, we're going to talk about that. We're also going to talk about some of the important things we need in order to be able to connect to the internet. And the first of these things is an IP address. So you've probably heard the term IP address before. What does it mean? Well, an IP address is basically a unique identifier of your computer on a network. Just like every home or office has a unique address to which one could send mail, similarly, does every computer, if it wants to receive data or send data, needs to have a unique address so that when information is sent or received, it's being sent from or received to the correct location. This addressing scheme, as I said, is called IP addressing. IP stands for Internet Protocol, which we'll talk about again, is called unique. Does every computer, if it wants to receive data or send data, needs to have a unique address so that when information is sent or received, it's being sent from or received to the correct location. This addressing scheme, as I said, is called IP addressing. IP stands for Internet Protocol, which we'll talk about again shortly. Now, E stands for Internet Protocol, which we'll talk about again shortly. Now, what does IP addressing look like? Well, the scheme basically was, when it was first implemented, to give every computer a unique 32-bit address. That's a lot of bits. That's 4 billion addresses. And generally, instead of using hexadecimal notation, which we've used previously in the context of pointers in C to talk about addresses, we usually represent IP addresses in a little bit more of a human-friendly way, representing them as 4 clusters of 8 bits, represented as decimal numbers, because humans don't frequently speak hexadecimal unless you're programming. But IP, people who use the internet aren't necessarily programmers, and so making it easy and accessible for them to be able to talk about what their IP address is, in case they maybe need to call up somebody to troubleshoot something, it's better to make it in the more common conventional decimal number format. And so an IP address just looks pretty much like this, w.x.y.z, where each one of those letters represents a non-negative value in the range of 0 to 255. Recall that an 8-bit number can hold 256 distinct values, and so that's why our range is 0 to 255, and we have 4 clusters of 8 bits, or for a grand total of 32 bits. And so an IP address might look something like this. This is sort of a generic default IP address, 123.45.67.89. All of them are in the range of 0 to 255, so that's a valid IP address. Here at Harvard University, all of our IP addresses start with 140.247. That's just the way that the IP addresses in this geographic area have been assigned. And so this might be an IP address that might exist here at Harvard. So as I said, if every IP address is 32 bits, we have about 4 billion to give out, a little more than 4 billion. But we can kind of see a problem, right? What's the world population right now? Well, it's somewhere north of 7 billion people. And in the Western world, at least, most people have more than one device capable of internet connectivity. I have one right here, and I have another one in my pocket, and I have one back in my office. So that's 3, and that doesn't even count the ones that I have at home, too. And so that's kind of a problem, right? We have at least 7 billion people and only 4 billion addresses, and every device is supposed to be uniquely identified. We have developed some workarounds to deal with this problem, something called a private IP address, which I'm not going to get into in this video, but basically allows for the web, the internet, to kind of fake out a little bit that you have a unique address by having private addresses and then funneling them through one single address, which is shared by many different computers. But that's really not a long-term fix. Even that fix isn't going to last forever, and so we need to have a different way of dealing with this. So as I said, we had about 4 billion, but that's not going to be good enough, right? And so the way that it has been decided that we're going to deal with this is to make longer IP addresses. Instead of 32-bit addresses, we're going to have 128-bit addresses. So instead of 4 billion addresses, we're going to have that huge number of addresses, which is 340 billion, 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 billion. So a lot of IP addresses. And this new scheme is called IPv6, is commonly how it's referred, the old scheme being IPv4. It's a bit of a problem in that this problem has been known about for a really long time. And we're really bad, apparently, and you'll see this a lot in the context of computers and computing, we're really bad at anticipating problems, or we're good at anticipating problems, but we're bad at dealing with them even though we know about them. So IPv6 has been around for a while, and only in the last couple years have we actually started phasing in these IPv6 addresses to phase out the IPv4 addresses. But some places do have them, and they look similar to a regular IP address, but they're a lot longer. So instead of now having 4 clusters of 8 bytes for your address, we now have 8 clusters of 16 bytes, and 8 times 16 is 128. And we represent these in the less conventional hexadecimal form, because having numbers, 16-bit numbers, means that instead of being a range of 0 to 255, we'd have a range of 0 to 65,535, and so having a bunch of those stuck together would be very difficult to read. And so we usually use hex just out of convenience. And so a typical IPv6 address might look something like this. It's certainly a lot longer than the IPv4 address we've seen before, but this would be a valid IPv6 address. This one is also a valid IPv6 address. This one happens to belong to Google. And notice there's a bunch of zeros there. Sometimes these addresses can get so long, and since we're still pretty early in IPv6, sometimes there can be big chunks of zeros in there that we don't need. That, if you're reading this out loud, it's 2001, 4860, 4860, 0000, 8844. It's kind of a lot, right? So if you see a bunch of zeros, you might sometimes see an IPv6 address like this, where they omit the zeros and use a double colon instead. This is okay, though, because we know that there are supposed to be 8 distinct chunks, and so by implication, we see 4. So we know that there must be 4 sets of zeros, like this, to fill it in. So sometimes you might see an IPv6 address not having 8 separated chunks like we do here. You might see it looking like this, and that just means that everything you don't see in between where that double colon is just 0 separated. So, okay, we know a little bit more about IP addresses now, but how do we get them? We can't just pick the one we want. If we did that, we might end up fighting somebody for the same IP address, or somebody might have chosen it previously. If we try and take it, we're going to run into a bit of a problem, and so we can't just pick the IP address that we want. So the way that we get an IP address is somewhere between our computer, but how do we get them? We can't just pick the one we want. If we did that, we might end up fighting somebody for the same IP address, or somebody might have chosen it previously. If we try and take it, we're going to run into a bit of a problem, and so we can't just pick the IP address that we want. So the way that we get an IP address is somewhere between our computer and the internet, that big internet out there. There's something called a DHCP server, a Dynamic Host Configuration Protocol server. It's a big mouthful of text, but really all it does is it assigns you an IP address. Your DHCP server has a list of addresses that it can validly assign, and it gives you one. That's pretty much all there is to it. Now, before DHCP, this task of assigning addresses fell to a system administrator. So an actual person would have to manually assign your computer an address when you connect it to a network. So DHCP just sort of automates this process of giving you an IP address. But that's how you get it. It's just a program running somewhere between you and the internet that has a bank of IP addresses that it can give out. And when you connect to the network, it gives you one. So let's revisit this diagram. Somewhere between you and the internet, there's a DHCP server. Okay, so that's good. Now let's talk about DNS. So we've talked all about these IP addresses, and we know that if we're going to uniquely identify a device on the internet, it has to have a unique address, and we could visit that address if we wanted to. But you've probably never typed in something like 192.168.1.1 into your browser, right? Like you don't type in numbers into your browser. You usually type in human readable names like google.com or cs50.harvard.edu, right? Those aren't IP addresses though. So there exists this server, or service rather, called the Domain Name System, DNS, that translates IP addresses to human comprehensible words and phrases that are much more memorable than remembering a set of 4 numbers, or soon a set of 8 hexadecimal numbers. That would be really challenging, right? Think about if you've ever been before the days of cell phones, you had to memorize your friends' phone numbers. It might have got tough after a little while, and similarly, if you want to visit a bunch of websites, you probably don't want to remember a bunch of numbers, you'd rather remember a bunch of words. So this mapping, this translating of sets of numbers to human readable names kind of makes DNS the yellow pages of the web, and you can think about it as if it's just a huge list running from 0.0.0.0 all the way down to 255.255.255.255, which would be the highest possible. That's the full range from there, from zeros to 255s of all 4 billion-ish IPv4 addresses. I made up the ones on the top and the bottom, but the one in the middle there is actually an IP address. So if we visited 74.125.202.138, apparently that translates to that site there, IO, what the heck is that? Well, not every name that maps is actually clear what it is, right? So sometimes somebody who owns an IP address might name their host something that they're actually not. For example, that IP address, if you went there, it's actually just google.com. But Google has a lot of different servers, and they can't call them all google.com, so they have their own internal system for translating google.com to whatever server actually is connected to that IP address. And then there's another system that exists between to translate that gobbledygook here to google.com, but we won't get into that. And similarly for IPv6s, we're also going to have a yellow pages. It'll be a lot bigger. And similarly in the middle there, it was tough to find an IPv6 address that was legitimate, but I found one for Google, but it's Google's Irish website. But if you went to that IPv6 address, if your browser was IPv6 capable, that would bring you to Google's Irish homepage. So there you go. But this isn't entirely true, right? This system seems cumbersome, right? If there's a huge list of 4 billion things to have to look up, that's pretty big, and there's no yellow pages of the world. Right? You don't go to you don't get, if you still get the yellow pages delivered to you. I got mine the other day and I just recycled it. But if you do get the yellow pages delivered to you, you don't get a book that's every phone number that exists on the planet, right? You get a list of the local phone numbers, the ones you're most likely to call. And that's actually what DNS is. If you think about it, DNS is really the local yellow pages. And large DNS servers like google.com's, they're actually just more like libraries that have a copy of all of the local yellow pages or all of the local DNS records. So there's really no one repository of the full DNS of the internet, just like there's no one yellow pages of the world. There are all these local, small-scale DNSs that exist out there, and there are services that aggregate them together, but they depend on those smaller DNS systems updating their information so that they have the most accurate information. So again, this analogy is large aggregating DNS systems are like libraries that have a copy of every yellow pages of the world. They don't themselves update those books, they depend on the books coming in so they can update the information if they need it. So the DNS system is not a giant block. It's decentralized across many, many servers. So now we know that somewhere between us and the internet there exists a DNS server as well as a DHCP server. Now, access points. What are access points? Well, access points you're probably pretty familiar with from actually connecting to the internet. That's the network that you choose, the home or your work network or what have you. And I'm generalizing the concept of an access point here for purposes of this video, but there are actually a lot of things that could be rolled up into access points. There are concepts of routers, which is sort of a general term that we use, but there are also switches and things actually called access points that are separate from this general concept of an access point. But basically what happens is with IPv4, I said we have this concept of private addresses, right? And instead of every machine having a unique IP address, which we have run out of because we're over 4 billion devices trying to connect to the internet, what we do is instead assign an IP address to a router, that router or access point that exists in your home, for example. And the router's job is to sort of act as a traffic cop, allowing everybody who's connected to that router to use the same IP address to get out. Does that make sense? So everybody at your home has a private IP address. They can't connect to the internet, or the internet rather can't speak to them through that private address. They can only speak to them through the address in the router, and it's the router's job to take information that you're sending the router and direct it to the correct place, and for information that's coming into the router, for the router to send it to you. So the routers are really the devices here, particularly a router. Common sort of usage case. For most people, the router in your home is the device that has the public IP address. That's the device that's connected to the internet. And you connect to the router to have information flow through it on your behalf. As I said, a modern home network, the router and switch and access point are all kind of bundled up into a single device. Sometimes a modem is bundled in there as well. That's usually just called a router, but it's really all of those things together. Large-scale business networks, or so-called wide area networks, WANs, actually keep these devices separate. They have a switch, they have routers, they have multiple access points. For example, at a university, you'll see things that look like so-called routers mounted all around campus. Those are all access points that flow into routers, switches, etc. to pass information along, because these networks are so big that one single access point can't cover its large area. And so these large networks, business networks, etc., split these into separate devices so the network can scale and grow if needed. So again, somewhere between us and the internet, we have an access point, and that's what we connect to. And through there, we can get to the internet. As I said at the beginning of this video, this is Not a course on networking, so this is not the entire story, and I've kind of glossed over it, and maybe I've left you a little bit confused as to what some of these things are, but that's okay. We don't need the whole story. It's enough for us to know, moving forward, just basically a little bit about how the internet works. So what we know is we have these private networks at our house, and we connect to a router, and that router is connected to the internet at large. We have these, but what is the internet at large? I keep saying this, but what is it? Well, it's really just all these individual networks at my house and at your house and at every other house that are connected together. It's an interconnected network, an internet. So instead of thinking about the internet as this giant cloud, this ethereal thing that exists out there, it's really just a connection among all of these networks. So here we go, we have our local network, and we're not the only person probably on our local network trying to use the internet. There's probably several of us trying to get in. And we're not the only network that exists in the world, right? There are other networks too that are trying to connect to the internet. But the internet is not, again, a separate entity. It's just a set of rules that allow these networks, these small networks, the blue, the purple, and the red network here, to communicate with each other. So there's no thing they're all connected to. They're all just connected to each other, right? And so somewhere on these networks exist the services that we actually want. So maybe in the blue network is where Google lives, and in the purple network is where Facebook lives, and in the red network, maybe that's where all those cats are. And so if we want to get information about cats, we just traverse this chain of networks to get the information we want. And it's not like the network, and here I've represented the networks as all being able to talk to each other, and we can only talk to the network, but the network can't talk back to us. But that's not true either, right? This is all a two-way street. Information can flow through networks back and forth. How does it do that? Well, the internet's really a system of protocols, and we're going to start talking about what those protocols are in future videos. But again, the internet is not a separate thing. It's a set of rules that defines how networks communicate, these small networks, these local networks that we're used to, the people in our house, the people at our school, the people at our job, all sharing a network, and how these networks interconnect and talk to each other. That's actually what the internet's all about. So let's, in a future video, talk about some of the protocols that comprise the internet to hopefully give you a bit more of a well-rounded understanding. I'm Doug Lloyd. This is CS50.
Wait, someone popped in? Hello? What? 3 minutes ago. Oh well.
If you watched our internet primer video, I left a bit of a cliffhanger, right, by talking about the internet and how it's a system of protocols. Well, let's talk about the first of those protocols that actually comprises the internet, and interestingly enough, it's called the Internet Protocol, which is usually referred to as IP. So the internet, as I said, is an interconnected network, an internet, which is really just several networks woven together and agreeing somehow to communicate with one another. What is this somehow I'm talking about? Well, this is the Internet Protocol. This dictates how information is transmitted from point A to point B, and this is sort of a condition of joining the network of the internet, is agreeing to follow this protocol when information needs to be moved from point A to point B. So at the very end of that Internet primer video, I showed this image of what the internet was. And on a part of the internet is agreeing to follow this protocol when information needs to be moved from point A to point B. So at the very end of that Internet primer video, I showed this image of what the internet was. And on a small scale, this is actually probably pretty accurate. This might be how 3 networks actually talk to each other. But it's a bit misleading. And the reason it's a bit misleading is because if I just number the networks for the sake of convenience here and we get rid of everything else and just focus on the networks, it's a bit misleading because it implies that all 3 networks have a connection to one another. 1 is connected to 2, 2 is connected to 3, and 3 is connected to 1. And when I talk about a connection here, I'm talking about a physical wired connection. We do have wireless, but it's really impractical for data to be transmitted wirelessly over a large scale, and so at some point, we really do rely on wired technology. Telephone wires, fiber optic wires, various technologies that are physically connecting point A to point B. And on a small scale like this might be accurate, but as the image gets a little bigger, let's now imagine we have 6 different networks. If that's true, now we have something like this for every network to be connected to every other network. And if you look, every network has 5 arrows connected to it, so everything is connected to every other network. But we only have 6 networks here, and already look at how much wiring we have to deploy, right? And the internet consists of a lot more than 6 networks. We can't afford to wire each network to each other network, especially considering some of these networks span oceans, right? If we're trying to connect to a network in Asia or in Europe, we're gonna have to span an entire ocean. If we need to, we're gonna need to use wires at some point, but we wanna minimize the number of wires we actually use. We don't wanna send 1 million wires across the ocean because they cost millions of dollars a piece to lie down. And so rapidly, we wouldn't be able to afford the internet anymore. So we have to have another way for every network to talk to every other network, or else we have pieces that are of the internet that are disconnected from other pieces of the internet, and that's not what we want. But we don't want to have them all wired together. And this is where routers come back into play. We can use routers in the following way. What if instead of every network being physically connected to every other network, we had these intermediary pieces where the networks were connected to these intermediaries, which were connected to a few networks. So instead of having 1 connect to 2, 3, 4, 5, and 6, maybe 1 connects to a router, which maybe connects to 1 or 2 of those networks, but also maybe connects to other routers, which also will connect to those other networks. And what the router's job is, it contains information called a routing table that dictates where do I go if I see a particular IP address. If I see an IP address starting with 4, I'm going to go this way. If I see an IP address starting with a 12, I'm going to go that way. We don't need to be connected physically to network number 4 or network number 12 in this example. We just know generally where we want to go. And if you think about it, this is sort of similar to the concept of recursion that we talked about when we were talking about it in C. I'm not going to connect you to exactly where you want to go. I'm just going to move you 1 step closer to where you want to go, and I'll let somebody else deal with solving the rest of the problem. I'll just solve this little piece of the problem and defer the rest of it to somebody else. So routing information is actually kind of similar to recursion. If that's a concept that you understand well, maybe that analogy would help. So let's take a look at this networking example again and assume that Again, we're going to use those same 6 networks, 1 through 6. So let's just say that every IP address on network 1 starts with 1 dot something. And we'll say that there's some other thing that deals with how to all the systems that are connected to network 1. We just care about connecting all of those networks together in an internet. So every device that is connected to network 1 has an IP address that starts with 1 dot and then 3 other numbers. This is a generalization of the way things actually work. It's quite a bit more precise than this, but this should give you a general idea of what the Internet Protocol is actually doing. So this was the diagram we had before. This was the system that was not sustainable. Even 6, this might be okay, but if we get to 10 or 20 or 50, we're going to be laying a lot of wires, and 50 is still also not even the tip of the iceberg as to the number of networks we have. So this model is unsustainable. We can't stick with this. So let's instead adopt this model where we get rid of all the wires between the networks and we add routers. So these yellow boxes represent routers, and their job is to move information generally closer to where it's supposed to go. And maybe these are the connections that these networks have, and maybe these are the tables that are built into the router. So if we just start by looking at network 1, for example. Basically, what it says is, if I ever see an address that doesn't start with a 1, that's what the exclamation point 1 or the bang 1 there, not 1, I'm going to pass it off to a router. And from there, the router can make a decision. The router says, if I see a 1, I'm going to move to network number 1. That's the green arrow heading to the left out of that top left box. If I see a 2, that's the arrow sort of heading to the top right towards the purple network. If I see an IP address starting with a 2, I'm going to go toward the 2 network. If I see a 3, a 4, a 5, or a 6, that's that red arrow coming out of the top left router. I'm not connected to 3, 4, 5, or 6, but I know somebody who is, or who's a little bit closer to there. So I'm just going to say, every time I see an IP address starting with 3, 4, 5, or 6, I'm just going to send it to that router. So I'll move it a little closer to where it's supposed to go, and let that router deal with the problem. And as you can see, if you wanted to pause here and trace, you can get to every other point in the network from wherever you are. All 6 networks can still connect to every other network, but they're not physically connected anymore. There are now these intermediate steps. Now, of course, there's a trade-off of speed, right? If 1 was directly connected to 6, we wouldn't have to go through 2 routers along the way, so we might be able to get the connection a little bit faster. But maybe that trade-off is worth it, right? If it's going to be so expensive in terms of actual cost, dollars and cents, to physically wire all these networks together, maybe a little bit of slowdown in speed is okay, we can tolerate that. So again, in that example we were just talking about, none of the networks were directly connected to each other at all. There could have been, maybe in that example, we could have made it so that maybe network 1 and 2 were directly connected, and that would be okay. Some networks are physically connected to other networks, but they're not all connected to each other. They rely on the routers in this particular example to distribute the communication from point A to point B. On a small scale, like what we're talking about here, this configuration actually might be more inefficient than just having direct connections. But on a large scale, we can scale the system a lot better. It's really going to reduce our costs of network infrastructure to have intermediary routers whose job it is to move traffic from the sender to the receiver or from point A to point B, as opposed to wiring everybody together. So let's take a look at an example of information traveling using this Internet Protocol. Let's say that I am physically located at IP 1.208.12.37, so I exist somewhere on the 1 network, and I want to send a message to you, and you're on the 5 network at 5.188.109.14. Your IP address specifically doesn't matter, but in this particular example, we're talking about this generalization of what the Internet Protocol is all about. You're on the 5 network, and I'm on the 1 network, and as you can see, we're not connected to each other at all. So I start out, and I want to send you a message, and so somehow I communicate that message to the router. The router is the one that actually has the IP address, and it's looking at where it's supposed to go. We're going to 5 dot something. So now I'm going to start using the router rather is going to start using its router table to pass information along. It sees that 5 is not 1, so it says, I'm going to pass it to this guy. Then this guy has to make a decision. Where am I going to go? Well, it's not a 1, so I'm not going to move to the 1 network, and it's not a 2, I'm not going to move to the 2 network, it starts with a 5. I'm not connected to 5, this router says, and so I'm just going to pass it off to, I'm going to go down this path. This is where 3s and 4s and 5s and 6s go, and I'll let that guy deal with it. I'll get it a little closer to where it's supposed to go. I know it's supposed to go in that general direction, but maybe that guy can deal with it. Okay, so that guy looks, he says, okay, this IP address starts with a 5. Well, I'm connected to 3 and to 6, so I can't get the message directly where it needs to go. But that other router over there, I know if I send it 4s and 5s, it can handle those. So it passes it along down the path. And then this router says, well, I'm connected to networks 4 and 5, so yes, I can help you. I'll take your IP address that starts with a 5, I'll give it to the 5 network. The 5 network will do some work on its end and give the message to you. And now we've successfully transmitted a message from me to you using the Internet Protocol. Again, very generalized for purposes of illustration as to what's happening, but that's pretty much how the Internet Protocol works. The routers know generally where to send it, and will send it one step along the way, getting it closer and closer to its destination until one router is physically connected to the network or the address or whatever in question and gives it there. Now, in general, except for really, really small messages, if it's not going to send it as one big chunk of data, right? If I'm sending you an email, a very long email, say, it's not going to take that entire email, bundle it up in a ball or a package or whatever, and send that entire thing down the network. First of all, sending information along the network is expensive. It does add up. And the larger the chunk, the more costly it is to move every step of the way. And if there's somehow a slowdown and there's this giant, sort of like if you're driving on the highway and there's this giant truck kind of blocking the way and you can't get around it on either lane because it's kind of spread out, it slows everybody else down behind it. But small cars, if they were all small cars, they might be able to move around. That analogy sort of helps a little bit. So one big block in the system can really slow everybody else down. And so what IP is going to do is split this data into packets. It's going to take this big email or FTP transfer, or file transfer, or maybe I'm making a request to a web browser because I want a picture of a cat. And it's going to take that request or that email or that file and break it up into many pieces and send all of the pieces separately. So in effect, I'm filling the highway with a lot of small cars which can all move instead of a big truck that might, if something goes wrong, throttle the traffic for everybody else. Another side effect of this is if there's some sort of catastrophic failure and a piece and something goes wrong and the packet gets dropped, something is failed and the message can't be communicated, the router maybe had too much stuff going in, it couldn't juggle everything, and so it just literally that's sort of the analogy, right? It's got a lot of things going on, it's passing information from point A to point B. We're not the only 2 people on the internet, so it has to process a lot of traffic. And if it doesn't have enough hands and it can't figure out what it's doing, it might just drop something so it can do something else. It's got too much going on. If we had our message as one huge block and that was what got dropped, now we have to send the message again, and we are now possibly causing traffic again, and we run the risk of that huge block being dropped again. But if the data's been broken up into packets and we drop one of those, it's a lot less costly to send that packet one more time as opposed to the entire thing one more time. So IP is responsible for getting information from point A to point B and also breaking the information into small pieces so that the network isn't overly taxed. IP is also known as a connectionless protocol. There is not necessarily a defined path from the sender to the receiver, or vice versa. Now, in this example we've talked about, there actually is only one way to get to every network. So in this particular illustration, there actually is a defined path from point A to point B, but we can change that by just making one modification to the two routers on the left by adding this condition to their router tables. Now notice that from the top left router, there are actually two ways to deal with a 4 or a 5 IP address. It can go down to the lower left router, or it can go to the right router. It has multiple options. And this is actually kind of a good thing, right? Because it makes our network more responsive. If, for example, it's sort of like a GPS. If you've ever been driving on the highway and suddenly your GPS warns you that traffic is ahead, you want to avoid it if you can, so you can recalculate your route. And the router tables, in addition to having information, or the router network rather, in addition to having information about where packets should go or where data should go, there's also sort of this general pulse on the state of its local network, what's going to happen if I send it down this path versus this path. And so in light of heavy traffic situations on the network, maybe things get routed a more inefficient way or a more generally inefficient way, because if we go the regular way, there's going to be a lot of traffic. The highway is completely jammed, so maybe what we'll do is instead take side roads, which ordinarily would take a lot more time, but no one's really using those side roads, and so we can route our packets that way. So not every packet of a big chunk of data might take the same path from the beginning to the end, and our network becomes a lot more responsive if our router tables allow there to be multiple options for where to go. We're not depending on that one truck moving out of the way. We can get off the highway at the next exit and take a different path. And so the Internet Protocol sort of does a little bit of that too. So that's the basics of the Internet Protocol. But there's one more issue to deal with, which is what happens if we do drop a packet? How do we know we're going to send that packet again, right? Well, Internet Protocol doesn't guarantee delivery. We're going to be depending on another protocol to deal with that, called Transmission Control Protocol, TCP, and we're going to talk about the Transmission Control Protocol in the next video. I'm Doug Lloyd. This is CS50. In this video, we're going to talk about the Transmission Control Protocol, TCP. If you haven't watched the video on Internet Protocol, IP, you may wish to do so before watching this video because the two are pretty interrelated. So the Internet Protocol, again, a quick summary, that's the protocol that moves information from a sending machine to a receiving machine through the network. So what's TCP? Well, just moving from a sending machine to a receiving machine isn't the full story. We also know that our computers, for example, are running multiple programs and have multiple services running on those machines. And so if we want to get a packet or information to a specific program on a specific machine, we need more information than just what IP allows us to get information from point A to point B. So TCP can be thought of as directing the packet to the correct program or the correct service on the receiving machine. And so it's important to, as you might expect, know where it's supposed to go and what the packet is for at the same time. And so frequently when you talk about Transmission Control Protocol, TCP, you really often hear it in the context TCP/IP or just TCP/IP. These two protocols are so interrelated that they are basically treated as a single unit, but they are two separate protocols that do two separate things. Again, IP is responsible for getting it from one machine to another, and TCP is responsible for getting it to the correct program or the correct service on a machine. And it does something else that IP doesn't do, which is guarantee delivery. So if we now couple a machine's IP address with a so-called port number, and a port number is how a specific service, a utility, or a program is identified on a machine. If we now have an IP address plus a port number, now we can uniquely identify a particular service running on a particular machine. So that's why TCP and IP are so frequently interrelated, because that port number on its own doesn't really mean anything if you need a port number and the machine that you're talking about, what machine is supposed to be using this particular port, for example. The other thing that TCP does, as I said, is it guarantees delivery. So in addition to specifying the port number, it also indicates how many packets the Internet Protocol IP has split the data into, and it orders those packets so that they can be reconstructed on the receiving machine, even if they are received in a different order than they were sent, which can happen because IP is a connectionless protocol, and so different packets can take different paths through the system. Some of these port numbers are very commonly used, and they've been standardized across all computers by pretty much every computer manufacturer. Can take different paths. Through the system. Some of these port numbers are very commonly used, and they've been standardized across all computers by pretty much every computer manufacturer now. So there's something called FTP, the File Transfer Protocol, which is used to transmit files, as you might expect, from one machine to another. That uses port 21 conventionally. Email, SMTP, uses port 25. DNS, the Domain Name System, which we talked about in our Internet Primer video, uses port 53. If you're ever browsing the web, you're pretty much always using port 80, unless you're browsing the web securely, secure web browsing, using port 443. So what's this TCP/IP process? What's happening with both of these protocols together? Well, let's talk about it. When a program wants to send data, TCP helps break it into chunks and communicates those packets to the computer's network software. So it takes the data and it wraps information around it that indicates what port it's supposed to go to and what order that packet is out of all. So my packet 1 of 10, 2 of 10, 3 of 10, and so on. IP gets those data chunks that have been wrapped with TCP and wraps more information about where the packet is supposed to go. We might call this the IP layer surrounding the packet. So it's sort of like one of those nesting dolls. We have the data in the middle, and then TCP on top of it, telling it where the data inside of TCP is supposed to go, to what port or what service on a machine. Around that is the IP layer. What IP address, what machine is actually getting this? So then that packet that's been wrapped with all those layers is sent through Internet Protocol, through the system of routers getting from point A to point B. When the receiving machine or device gets it, it looks at the IP layer and says, yep, that's my IP address. So it takes off, sort of cracks the egg and takes off the IP layer. Then it sees that there's a TCP layer. And it says, okay, it looks like this is going to port X or port Y. And apparently it's packet number 8 of 15. So that's good to know. So then it can take that information, take off the TCP layer, now knowing that it's for port X and it's packet number 8. And it can get at the data inside, and it can prepare the data to be organized in the correct way. And once all of the data is received, TCP can hand it off to the correct service and say, here you go, here's the data that you received. So that process might look something like this. So let's send an email from a sender to a receiver. Now let's say this email is pretty small, so we only need to break it into 4 packets, and we'll call them A, B, C, and D. Well, when we want to move that first packet, what happens? Well, we take that chunk of data, the data that is part of packet A, and around that we're going to wrap it with a TCP layer. Emails, you may recall, are sent via port 25, and we have 4 chunks of data here that we're going to be using, and this is the first of them. So maybe our TCP layer contains information about, well, we're going to port 25, and this is packet number 1 of 4. Around that, so now we have all that information bundled up together, we're going to say where we want it to go, what machine, what IP address is supposed to get this packet. And that's part of the IP layer. And there's other information in there as well, such as the return address in case something goes wrong, it knows where to send information back and so on. But the IP layer goes around all of that. that entire thing is bundled together as one big unit and sent through an IP transfer. So it gets routed through the router network using Internet Protocol, and the receiver receives the entire thing. And then it can start to deconstruct what's happening here. It looks at the IP layer, the outside layer of this data, and says, yep, that's my IP address, so it can discard that, it can kind of ignore it, doesn't need it anymore, and can look one level deeper. It sees that, okay, this is data that is intended to be received on port 25. It's apparently the first part of 4. So I'm going to keep that in mind and look at the data and slot it roughly where I think it's going to go. Now, because of the Internet Protocol, it's not necessarily the case that the next packet the receiver gets is packet 2. In fact, the next thing the receiver gets might be packet number 3, because these packets took different paths because of different traffic on the network. And so I'm not going to go through the diagram of building it up again, but packet 3 moves, gets stripped away of all of its layers, the IP layer, the TCP layer, and the data gets put in the right spot. And then let's say it receives packet 4. Now let's say that's it. It doesn't get any more data. Well, what is it going to do? Well, IP doesn't do anything for us, but TCP does. TCP knows, well, I've received 1 of 4, 3 of 4, and 4 of 4. I'm not getting any more data, so something has gone wrong. But I can guarantee delivery. I know that packet number 2 is missing. And so TCP can now make a request sort of in the reverse direction, bundling up its request in much the same way and sending it via IP, which I know could lead to some sort of infinite loop of everybody dropping packets along the way. But suffice it to say that TCP says, I'm missing a packet, I need to send information back to the sender. Fortunately, the sender's IP address is sort of bundled up in the IP layer. It's part of it's the return address of the envelope, say. And say, I'm missing packet number 2, can you please resend it? When the sender receives that information, it doesn't have to send the entire email again. It only needs to send that individual piece of it that was missing, so it can send it packet number 2. And when it gets it, now TCP says, I have all 4 pieces of data that I need. So I can assemble them together and take this entire block of information and pass it along to port 25, where it will be interpreted as an email. And that, in this way, we've now sent an email from sender to receiver using TCP IP. So as I said, if any point along the way something went wrong, TCP can deal with it. It can make a request that the information gets sent back to it, and it can reconstruct the message. And once it's reconstructed the message from all of the packets it's received, then it can organize them and deliver them to the correct service. So that's TCP in a nutshell. That's how we guarantee delivery of information. Remember that TCP frequently works with IP, so these two protocols really do go hand in hand. We discussed them in separate videos here because they do different things, but they're so interrelated that you'll usually use them together. I'm Doug Lloyd. This is CS50. Let's talk about another protocol, the Hypertext Transfer Protocol, or HTTP. So we've talked about IP and TCP in previous videos, and those are protocols that dictate how information moves from machine to machine and from program to program or service to service via the internet, via this network of routers and machines. But that's usually not the entire picture, right? Usually when we send information, the program itself, when data is received, say for example an email via TCP port 25 or a web page request via port 80, there's usually a system of rules there to process what I've just received. And HTTP is an example of just such a protocol. HTTP is the only application layer protocol that we're going to talk about, but it is another set of rules. dictating how information is to be transmitted and processed via the internet. In particular, HTTP specifies exactly how one must make a request for a web page and exactly how a server, a machine that hosts web pages, delivers that information back to clients. So this protocol doesn't actually have anything to do with how information moves from point A to point B. It's really the system of rules it's basically the rules of engagement for working with a web page. Similar to when somebody waves their hand at you, you're supposed to wave back. That's sort of a conventional human protocol. An HTTP protocol just says, if you want to request a web page, make sure your format looks like this, sort of like formatting a business letter, for example. And the response will similarly come according to this protocol. There are other application layer protocols that we're not going to talk about in videos, but these include things like the file transfer protocol, simple mail transfer protocol for sending emails, the data distribution service, remote desktop protocol, RDP, which is used if you want to remotely access your computer from another computer, XMPP, which is frequently known as Jabber or Chat. This is the protocol for using chat services, and there are many, many, many others. So every time you're using a service, the service is expecting information to be received or requests to be received in a very particular format, and is required to return information back in a very particular format as well. So let's go back to our illustration of us wanting to talk to the internet. So we're happy and we want to go to cats.com, right? So if we're just talking to cats.com, we might say something like, hey, can I see your homepage? And cats.com will probably respond, yeah, sure, here you go. So that's a human sort of ask and answer. What does that look like in HTTP? Well, it actually kind of translates pretty cleanly to something like this. We might say get/HTTP/1.1 from host cats.com. So basically what I'm doing here is asking for the web page www.cats.com/. We usually omit the slash nowadays, but that would just mean cats.com's homepage. Oh, and by the way, I'm going to be using HTTP protocol, or HTTP version 1.1 to communicate with you. That's sort of analogous to saying, like, by the way, I'm going to be speaking in French, or by the way, I'm going to be speaking in English. That's just the format of the protocol. There's also 1.0, which is not commonly used anymore. So I'm speaking HTTP 1.1, and I would like www.cats.com/. Please get that for me. And then there's other information too, the ... there, which is information about who you are, so cats.com would know where to send it. But these are the two sort of critical parts at the very beginning of an HTTP request. Just like when you start a letter, you say, dear blank. This is very similar in spirit to that. And if cats.com is going to say, oh sure, here you go, they might respond like this. I'm also responding. I also speak HTTP 1.1. Your request is approved. It's 200 OK. What you're about to receive is HTML, and then ... some extra information. And at the very bottom of the request is actually the HTML, the markup language, the content of cats.com's homepage. So HTTP/1.1, I acknowledge your request was accepted via HTTP 1.1. Your request was approved. I can give you what you want, 200 OK. You're about to receive HTML, and then here's the HTML that you requested. But sometimes our requests don't always go quite according to plan. Can I see your cats.html page? Well, what if they say, we don't have a cats.html page, which seems kind of unrealistic because they're cats.com. You'd think they would have cats.html, but okay, so this is sort of the conventional human interaction we now have with cats.com. How does that translate? This might be something familiar to you. Our request looks exactly the same, except instead of getting /, we're now getting cats.html. So now what basically this entire request is saying is, please give me www.cats.com/cats.html. So the host and the middle part of that top line there indicate precisely what page I am asking for. But cats.com in this case isn't going to be able to respond positively. They don't know what we're talking about. And so this is something you might have seen before. HTTP 1.1 404 not found. I couldn't find what you were asking for. By the way, I'm going to give you back some HTML, and usually that HTML is the content of some 404 page. And in the case of cats.com, it's probably some cute cats in a basket with a sad 404 face next to them, because you're going to be sad when you don't get the page that you were looking for. But that's kind of the basics of what the HTTP protocol requests look like. They're fairly similar to how we would make a similar interaction in just human conventions, asking for something and getting it back, or writing a letter and expecting a response letter in a particular format, that's pretty much what HTTP is just canonicalizing for all devices that wish to access web pages, hypertext transfers. So a line of the form this, the method request target HTTP version, is called an HTTP request line. It's usually the first thing that is transmitted as part of an HTTP request, or if you're asking for HTTP. It's sort of like, as I said, saying dear blank at the top of your letter. They know that you're writing them a letter. So this is very similar to saying, I know that they're making an HTTP request and this is the particular format they're asking for. HTTP version is probably always going to be HTTP/1.1. 1.0 also exists but isn't really used anymore. For purposes of CS50, GET is probably always what you're going to be using when you're actually making direct HTTP requests. But post is another option that we're not going to talk about right now. 1.1. This is very similar to saying, I know that they're making an HTTP request and this is the particular format they're asking for. HTTP version is probably always going to be HTTP/1.1. 1.0 also exists but isn't really used anymore. As I said, that host name is a separate line, usually the second line of the overall request, and so taken together, the host name and the request target specify a specific resource being sought. In our 404 example a second ago, I was asking again for www.cats.com, cats.com being the host, and in my request line, I said /cats.html. That was my request target. So overall, I was asking for the contents or the resource located at www.cats.com/cats.html. And then based on whether the resource exists and whether the server can deliver the resource pursuant to the client's request, you might get various status codes back. Some of these status codes you've seen because they're part of the response. You might get various status codes back. Some of these status name is a separate line, usually the second line of the overall request, and so taken together, the host name and the request target specify a specific resource being sought. In our 404 example a second ago, I was asking again for www.cats.com, cats.com being the host, and in my request line, I said /cats.html. That was my request target. So overall, I was asking for the contents or the resource located at www.cats.com/cats.html. And then based on whether the resource exists and whether the server can deliver the resource pursuant to the client's request, you might get various status codes back. Some of these status codes you've seen because they're part of the response. Some of them, like 200 OK, are probably pretty silent. You've probably never seen a page respond 200 OK, you just get the page. It's not like 404 error, which is usually pretty clear. You usually see that it says 404. So let's talk about what some of those status codes might be. Again, when the server responds to us, they're going to respond HTTP version status, usually HTTP 1.1. What are these status codes going to be? Well, we might get success. So in the success category, we might get going to big status, usually HTTP 1.1. What are these status codes going to be? Well, we might get success. So in the success category, we might get code 200 with the text OK. What does this mean? Well, everything is good. You made a valid request. Here's a valid response. I was able to deliver exactly what you wanted. Sometimes you might get other things that you won't notice right away, but are somewhat failures. They're called redirections. There's two common ones here. 301, moved permanently. What this basically means is the page is now at a new location. It will live there forever, and most browsers will automatically redirect you. So you'll never really see a 301 either, unless you're using a really out-of-date browser possibly, because the 301 response as part of the ... of the 301 response, it also tells you where the new page is, and so most browsers will just redirect you there, assuming that you want to go there. Sometimes you'll also get 302 found, and this one you actually might still see occasionally. Sometimes pages move temporarily, so it's not going to be built into the request, telling the browser to permanently change anytime it sees the request that you make to change it to something else. So you might see 302 found, which basically says this page lives somewhere else, but it's not going to live there forever. It'll eventually probably go back to where you think it is. Then you'll get things like client errors. So these are ones you've probably seen now. You probably haven't seen the 200s or the 300s, but you're probably familiar with the 400s, as we'll talk about in a second, and 500s as well. You might see 401 unauthorized. Usually this means you're trying to access a page, but you haven't logged in. So you try and go to some profile or something on Facebook, or you try and access some, you're at work, you're trying to access something on your work's intranet, but you're not logged in, you can't see the page. You might get a 401 unauthorized, which means we probably will be able to satisfy this request, but first you need to log in to do so. Conversely, you might get 403 forbidden, which is it doesn't really matter if you're logged in or not. This request isn't allowed. The resource exists on the server, but you are not allowed to access it. This is usually internal files that live on the server for various reasons, but are not intended to be accessed from the outside world, so they are forbidden. They live there. I'm not saying I can't find it, but I'm saying I cannot give it to you, and it doesn't matter if you're logged in or not. And then, of course, the very common 404 not found. If the file doesn't exist on the server, I would like to satisfy your request, but I can't. You'll also sometimes see server errors, the most common general one being 500 internal server error, which doesn't actually tell you anything at all about what has gone wrong. But it's not actually you making a mistake in your request, it's actually the server failing to deliver on the request somehow. So 500 is the general response. You'll also see something like service unavailable, which I believe is code 503. And gateway timeout, if you ever had a page just sit there loading and loading and loading, and you never know if it's going to load, and then eventually just says, just gives up. That's a 504 gateway timeout. The server wanted to execute your request, but something went wrong on the server side, not on your side, to cause that to be a problem. Now, we could end the story here, but what I'm actually going to do now is I'm going to open up my browser and show you how you might be able to see some of these status codes, even if you don't generally see them. And we're going to do that by taking a look at some developer tools. All right, so here I am now in my browser window, and I want to learn a little bit more about these HTTP requests. How do I know? Certainly we know if something goes wrong, we get a 404. We've all seen that. We don't need to illustrate that. But what are some other ones, and how would we see these requests in action? So first thing I'm going to do is open up developer tools. The developer tools are built into most modern browsers and allow us to see things that we don't otherwise see, some extra information sort of being transmitted underneath our web requests. I'm using Google Chrome here, and to open developer tools in Chrome, you just hit F12, and it's going to open it up on the side. Once I type the request, I'll zoom in so we can see what's going on here. But what I'm going to do in my browser bar is, and I'll zoom in over here, I will make a request to www.google.com. We've all probably made this request before. I'm going to hit enter. Now, over here in my developer tools, I've chosen the network tab. And you notice a lot of things here. Look at these, 200 OK, 200 OK, some of these status codes coming up. I don't know why I'm getting a 302 found, I didn't realize I'd see that one. But basically notice that pretty much, in terms of my Google request, I made a very simple request for Google's page, and in the process of delivering my request, Google has apparently made a lot of other requests on my behalf. But yeah, I've made a GET request for Google's page, and I'm getting a lot of 200 OKs. I'm not seeing 200 OK on my screen, but I'm getting a lot of requests that have been made. One more that I'm pretty sure is going to work is, for those of you who are really old school, you may know that Facebook was not always at facebook.com. In its early days, it was at www.thefacebook.com. They apparently could not get access to facebook.com for quite a while. And so what I'm expecting here is to get information, and we'll see if this pans out. What I'm expecting here is to get information that Facebook has moved permanently from thefacebook.com to facebook.com. So I'm expecting somewhere near the top of my requests over in my developer tools to get a 301 notification that Facebook has moved permanently. Again, I won't see 301 on my browser screen. And because it's a 301, it's a permanent move, my browser, being that it's a modern browser, is probably going to redirect me to facebook.com anyway. But let's see what happens. So now I'm going to go to thefacebook.com, and yep, there it is right at the top. Oh, it went away, but it was there. Let me scroll up here. right here at the top, I made a request to thefacebook.com, and I'm getting a response that this page has moved permanently. And then 307 here is an internal redirect, and so this is what has actually moved me to the much more familiar www.facebook.com. So these response codes do still happen even if we don't see them. I'm not going to illustrate 401, 403, 404 because you've probably seen those at various points. And 500, I would just be kind of, we get lucky if we got a 500 because I don't know what servers are currently down anywhere. But these codes do exist, and there is a way to access them even if we don't see them firsthand on our systems. I'm Doug Lloyd. This is CS50.